Welcome, this is a recorded session of the Post-Quantum Cryptography Conference of the PKI Consortium. This conference would not have been possible without our sponsors, PQ Shield, SSL.com, Entrust, Keyfactor, HID Global, and the organizational support of the Post-Quantum Cryptography Working Group of the PKI Consortium, and in particular, Entrust, Keyfactor, and Logius. Would you like to join the PKI Consortium? Go to pkic.org/join, or contact us if you would like to become a sponsor.
Okay, so we have one more conversation or one more presentation before the lunch break on updating end-to-end PKI and HSM integrations with ML-DSA. It's my pleasure to introduce Tomas Gustavsson, the CTO of Keyfactor. Tomas, without further ado, I'll turn it over to you.
Thank you. Your Swedish is excellent. Okay, I'll keep you awake before lunch, hopefully. We'll see how that goes. So let's see. Here's the clicker, and I'm just waiting for the slides to show up. Well, I'm Tomas Gustavsson. I work with PKI since a long time, and one of the things I'm doing is develop PKI and try to integrate it into fuller systems. And in this case, I've been playing around with a bunch of HSMs. Okay, a recap. We've done this before, comparing HSM and algorithm speeds, signature speeds. So this was from the PKIC or PQC Conference in 2023. We did some tests with Dilithium on different HSMs. So, and certificate issuance with HSMs as well. But now, of course, we want to move away from all that old stuff. So now we have the standards, of course, that we're all talking about here, and we need to start thinking seriously, how do we move into production, and then we need to test the final algorithms and everything like that. And that's what we've been doing. So, kind of with these standards out, this is, we want to start to put things together, and building on what Mike was just presenting, we want to start to migrate to, complete solutions, something like this. We want to have a PKI that issues post-quantum certificates to web servers, Apache, Nginx, IIS, that's one of the questions touched on as well. Both some client that you can communicate, both client and server certificates, maybe SMIME, where we use both, say, ML-DSA for signatures, but also ML-Chem for encryption. And of course, one of the first anticipated use cases is code signing, where typically, of course, you want to have a PKI that can issue code signing certificates, something that signs code, and something like OpenSSL, which is a common component for, say, a firewall that actually verifies the downloaded signed firmware to do that. So, this is what we want to, if we want to do a practical actual migration, we have to put all these components together. But, well, let's focus on the PKI at least. That's kind of the part that I can control. And then I can branch out to the other stuff. And when it comes to PKI, it is important that all PKI and digital signature solutions in production, I would say, always use an HSMs, basically. So, and that's why I'm here. And there are differences between different HSMs, though. So we will, for example, if we use a soft HSM for development or testing, it's all in memory, right? So there's no latency, ultra fast. PCI HSMs also kind of used in memory because the PCI bus in a typical PC communicates over shared memory and stuff like that. So instant, fast, no constraints. Then we have more commonly network-based HSMs, where there you actually pass a network stack and maybe a local area network. So there is latency in there. Not super much if it's close by and you have a fast network, but still there is latency. And then finally, becoming a very popular option nowadays are cloud HSMs, where you actually pass over the internet. So you can have significant latency. So I did a lot of testing, for example, across the Atlantic Ocean, which has latency. It can still be fast, but it's All these have very different, or not very different, but definitely different characteristics, and you can expect different things with it. And this is something that Mike has been working a lot with on the IETF. You know, there is a reason why hash and sign is efficient, like we do with SHA-256 with RSA or ECDSA, because you hash it with SHA-256, you get a short piece of data and send over the network. It's going to be efficient, or even, you know, for a cloud HSM on the other side of the planet. But there is also a reason why hash and sign is legacy, which has everything from usability reasons or the ability of users to choose the right combinations of components. So, like, let's not combine SHA-1 and RSA 4096, for example, because there's a lot of bad things that can be done if you don't really know what you're doing. And I wouldn't even claim that I do know that myself even, so even less a lot of normal users. So, adding to that, there are basically two major ways today that we talk to HSMs. The first one is PKCS 11, that has been around since the 90s sometime, where you have a, you know, your application talks to a local PKCS 11 client, which you get from the HSM vendor. And this is, you know, custom for every HSM vendor. They deliver it, it's proprietary. And then the PKCS 11 client is configured to talk securely to the HSM wherever it is. So you depend on those components. It works good because PKCS 11 is a standardized interface. You code once, runs everywhere, kind of. But it's, say, in a modern cloud-native environment, people are not super thrilled coding against the C API, and you also have to install these local components that you get from the HSM vendor into your containerized environment and such, which can be, I mean, it becomes a little bit messy if you want to keep it clean. So another popularizing way to talk to HSMs is REST-based APIs or something similar, where you code it into your application, as kind of a lot of developers today are used to do. You code for a REST-based API endpoint into your application, and well, boom, you're done. You can talk to your cloud HSMs or local HSMs or whatever. So those are the two main reasons. They do have a slightly different characteristics. But without further ado, let's get into the practice. I will, you know, show the data first, and then get into some discussions before. I will reveal already now that I was definitely slightly over-optimistic when getting into this or submitting this speak. I was assuming that, well, by January, you know, all HSMs will have ML-DSA implemented, and I will have done everything fine as well, and we'll be in production. I was slightly over-optimistic, I admit, even from my own side. So I, since not all HSMs support ML-DSA or FIPS 204 final yet, for example, I decided to throw LMS into the game as well, which did give some interesting results. So let's go. So the first HSM that I tested, a REST-based API remotely over the internet. Not super big latency within Europe. Actually, this was the first one which I got support for all algorithms for. So you can see that performance for classic algorithms like RSA, EC, and new ones like ML-DSA is the same, which is now this, which just means probably that the HSM isn't a bottleneck. Absolutely not. So I'm actually issuing certificates here, not testing the maximum signature performance of the HSM. So this is, you know, a couple of tens of certificates per second here. When moving to LMS, you
is the performance better or worse as it goes to the right?
right, longer is higher.
Okay, so it's a little faster.
Yeah.
Okay.
Exactly, longer is higher. I'm not going to reveal vendor or actual numbers because that's not why we're here. LMS actually works as well, pretty good. It could even handle parallel requests. In my testing, I run multiple threads, like between 10 and 50 parallel threads to the HSM to, you know, at least use the system some. LMS, I could get half of that, which was not bad, you know. And the HSM, of course, handles all the state management that we heard about from NIST, which is a nightmare. But HSM2, also a over the internet, a REST-based HSM. Here we actually have quite good performance on classic algorithms, something like 300 certificates per second issued, even with internet latency. Doesn't have ML-DSA yet, coming in a couple of months. LMS, you know, it works, but its performance is meager. So if it's the long ones are 300, you know, the LMS there is less than 5. And it doesn't handle parallel requests. You get errors if you try to send 2 requests at the same time. So you really have to streamline or serialize your request to that. HSM3, another one remotely over the internet, but using PKCS 11. Also fairly good performance with classic algorithms. I think this was maybe like 70 certificates per second or something like that. ML-DSA also not available yet. But LMS is. But its performance is even worse. You can get, well, no parallel requests. You only one request at a time, otherwise you get errors. And it actually does less than 1 signature per second. So we'll discuss that a little bit later. Oh, HSM number 4. This is a container-based emulator or simulator of the HSM, so you can use for testing before going to the production HSM. Also quite good for P2EC and ML-DSA. It's actually several hundred, I think it's like 200 certificates per second. LMS works also with parallel requests, but fairly slow, less than 10. And the final one, which is a software-based, basically a soft HSM, which just runs locally on my laptop and has you know, something like 300-400 certificates per second across all algorithms. So it's fairly good. This one doesn't have LMS though, so mileage definitely varies a lot here. So, well, what I'm happy with is that it actually works. Your mileage varies, but things do work when you get it together. So to make it a bit more interesting, I threw also in kind of signing size, because now has been a lot or bit of development in the IETF when it comes to sizes. And specifically, you know, if you're signing certificates are typically small-ish. Well, unless they get bigger when you throw in things like ML-DSA 87, right? But CRLs are small to quite large. Bank transactions, kind of small. Documents, small to medium, and firmware signing can definitely be large to huge, I would say. And getting back to what I said in the beginning, there is definitely a limit on the data that you can stream to a network-based HSM and expect it to work, right? And some popular options on the cloud HSM front actually today have a 4 kilobyte limit of the signature payload. So if you want to sign something that is more than 4 kilobytes, well, then your only option is to hash it first and only sign the hash. And of course, the new algorithms I crossed out there are, because they were, thanks to Mike's work in the IETF, there are some options, at least for ML-DSA, just sign, right, and not sign hash and sign. So for ML-DSA, pure ML-DSA, you're supposed to sign the data, send the data to be signed and you get the signature back. That's how it works. So testing some sizes as well. So I tried where ML-DSA and LMS was available. I tried both. Where only one was available, I tried that one. But regardless, where both are available, there were no differences, same limits, right? So the first HSM had a limit of 1 megabyte signing payload, approximately 15,000 revocation entries in a CRL. HSM2, lower limit, 360 kilobyte. HSM3, PKCS 11 based, doesn't matter which mode you do it in, if you send the whole payload in a single buffer, or if you use the update mechanism in P11 and send it chunk by chunk. So it doesn't matter. 120 kilobyte, only like 2,000 revocation entries. HSM4 actually pretty good. Now we're 14 megabytes, and HSM5, which was just a local soft HSM that doesn't have any limit, just streams over memory. Actually, well, I stopped testing at 600 megabytes with more than 10 million entries. But as you see, the differences are quite large. So if you have a solution like this and you want to, architect your migration to PQC, you have to know, well, currently, you have to know what you're doing and how your solution is going to look, what your revocation pattern is going to be, etc. So we'll see changes in the future, but this is definitely the current state of the art. So some lessons learned, I would say. When it comes to sizes, the draft, which almost reaches RFC soon, hopefully, for using Dilithium or ML-DSA in certificates, have introduced a external MU ML-DSA to cope with larger data. So this will hopefully, come to fruition soon and eventually be usable by HSMs. The nice thing with this is that will sign in different ways, but if you want to verify something, it's the same algorithm. It's still ML-DSA. So in contrast to what the situation that is currently with if you want to do ED-DSA, there is ED25519 or pre-hash ED25519, which is not very fun, and it's not easy for users who are putting things into production or designing their architecture to understand what they're doing. So we don't want that. For signing, though, CMS or cryptographic message syntax always had a workaround. If you use signed attributes in a CMS message, you always hash message and attributes and sign that. So the workaround is easy. Always include some signed attributes and you're good to go. But as also Mike pointed out, there's lots of other signature formats, and how does that work with other signature formats? So that's some questions. And one thing I stumbled on when playing, of course, with ML-DSA was that some implementations started calling things ML-DSA when it was still actually what they call initial public draft in the draft period. And it turned out NIST changed something before they released FIPS 204 final. So if you just look at the API and say, oh, I'll actually sign with ML-DSA, but what you get back, you can't verify with ML-DSA because it wasn't ML-DSA. So this is, of course, is something that is going to solve itself in a couple of months, right? But when you do initial testing or did initial testing for a couple of months ago, this can cause confusion. When it comes to APIs to HSMs, we do have PKCS 11 version 3.1, which is the latest version currently available, that does have LMS in it. And it does work. I could code once and it works on all the P11 HSMs that support LMS. Good news. For ML-DSA, we do have a draft. It's going to be included in PKCS 11 version 3.2, and good news there as well. So after communicating and get some patches from the few HSM vendors that support this, it seems to be working as well. So this is good signs for the future. If we use PKCS 11 version 3.2, which is now in draft, things can expect to actually work quite interoperable. With the exception of external MU ML-DSA, which is kind of still up in the air. But with size constraints, this works. REST-based APIs are, you code towards a REST API, which is at least familiar with the, say, modern young developers. The downside is that you have to code specifically for each HSM because there is no standard for it. So you do something that fits that HSM and you have to repeat it if you want to play with other HSMs. So getting to the final conclusions. So some could say issues encountered. One I did was also has to do with how standards have changed recently. The public key encoding of LMS or HSS keys actually changed from octet string to bit string not too long ago, or was it the other way around? So that actually caused one interoperability snag, which was quickly fixed, of course. And also they stumbled on some small snags on the signature when it came to LMS versus HSS. And supposedly ACVP testing only have LMS signatures, so you have to consider that at least. But the most interesting thing when it comes to LMS is, if you were downstairs a couple of hours ago and heard NIST talking about it, it was supposed to be a stopgap measure with stateful hash-based signature algorithms. I couldn't agree more, because the results are inconsistent, slow to very slow, multi-threaded or not. If you want to use stateful hash-based signature algorithms, expect to do some work. You can't just, throw in LMS and expect it to work anything similar to other things that you have been doing. So you really have to expect that to take extra time and architecture and everything like that. So if you would ask me to point a finger, I would say, well, if you can, avoid LMS. When it comes to ML-DSA, I already mentioned, the transition period from draft to final standards, but it's going to solve itself, of course. No one's going to care about the draft version soon. There's this ML-DSA versus hash ML-DSA or signing LAR data, which is kind of a bit too late to the game. So we're not there today, I would say, to sign large data with ML-DSA with HSMs, but hopefully that would also be sorted out in the future. But if you want to do something today, this is something that you have to think about, how to sign large data and not just expect it to work like SHA-256 with ECDSA. And the conclusion, wow, start to encrypt like it's 2030, I think. There's been some issues when you do testing, but actually I think the future, our future looks bright. So inconsistencies and testing things aside, it does look good. Start testing early and of course focus on ML-DSA and forget about the draft algorithms and anything like that. And yeah, test on. Thank you.
Thank you, Tomas. That was fantastic. A lot of great information in that presentation. It is time for lunch. Do we want to take one question from the audience or no questions? We need to move for lunch? Okay, very well. I would just encourage you to take advantage of Tomas during the breaks. I'm sure there are plenty of questions off his presentation. So, Tomas, thank you very much. Fantastic. Well done, well done.